Hello everyone, my name is Hui Huang from Yuanzi University in Taiwan. Here I'm presenting my own work, Muscle-Aware Motion Prediction with Digital Humans. As the global population continues to age, the demand for the advanced rehabilitation techniques or systems is increasing. So in order to build such a better rehabilitation system, we can try, the most important thing is to understand how we move, such as the task of motion understanding or motion prediction. But in this kind of motion prediction task, most of the works are only focusing on modeling the skeletal body joint sequences, and the muscle informations is often ignored in this kind of modeling systems. So in our work, we are trying to integrate this type of muscle informations to the motion prediction task. So we are trying to incorporate this type of motion information into this motion prediction task to make it more accurate and with the aim to increase the biomechanical interpretability. And in our work, for the moment, we only focus on the walking-related motions, and we conduct our experiments on the human 3.6 million data sets. So in terms of incorporating this kind of muscle informations, the ideal way is to apply with the digital human model to simulate the realistic human movements, such as using the OpenScene software to do that. But as you may know, the OpenScene software is not differentiable for our neural networks. So it is hard to incorporate that information into this kind of model training. So instead of that, we try to apply the techniques of inverse dynamics to extract the muscle-informed features by taking the information from our body joints coordinates. So in our work, we utilize the dummy muscle information as the muscle activations to train the model to help on the motion prediction task. So as our baseline model, we take the Oxformer from ICCV 2023. So that is a transformer-based model taking the input motion with different body joints coordinates, and then to predict the future motion in the way of body joints position. So they utilize different types of techniques to improve the learning of this motion prediction task. So this model serves as our baseline model for this motion prediction task. So on top of that, we try to estimate this kind of muscle information by calculating the distance between these lower body joints, like the left knee, left thigh, and then trying to incorporate into our baseline model. So we designed a small decoder on top of this Oxformer model to predict this type of muscle activations. The decoder is composed of 2 linear layers and 1 sigmoid layer to predict this final muscle activation. So the overall work is acting as a multitasking network. So with this additional decoder, we aim to make this model learns better to have a more accurate motion prediction. So in our experiments, we utilize the human 3.6 million data sets as our test bench. And as you may know, in this data set, there are multiple participants doing this type of different motions. And then we try to capture the body joints positions as is as the data. But in order to test our proposed model to see if the muscle information helps, we focus on the walking related sequences like walking with dog and walking together. To evaluate, we calculate the MPJPE matrix to see if the motion prediction is accurate or not. So here is our quantitative results. Each table presents one specific motion from walking, walking dog, and walking together. And for each row, we have first one as the baseline numbers, and then the second row shows after incorporating this muscle information and what is the corresponding MPJPE number. And sorry, I forgot to put the header in this table. For each column, it shows the short sequence at the future time step, like 40 millisecond, 80 millisecond, 160 millisecond, and 320 millisecond. And the last column shows the average number of these different MPJPE numbers. As you can see from these tables, for the walking motion and the walking together motion, our muscle information actually helps. It gets a lower MPJPE value, which is better in terms of this accuracy. But with this walking dog motion, we didn't get better results, as this kind of motion is quite a little bit complex because we have the dog incorporated into this motion. It might be confusing for the model to learn a better representation. So for the moment, we are trying to incorporate better methods to improve this type of motion to make our text better. So with this type of model, we aim to apply it into the rehabilitation systems, trying to make our motions more interpretable, and in order to build a better rehabilitation systems to make the patient to have a better feedback. And we can also incorporate this kind of systems into VR or AR systems to enhance the realism and physical feedback, as well as the HCI human or human-robot interaction parts. As a future work, we aim to integrate the OpenSync into our model training in the forward simulation part, and we aim to extend it to the real-time VR-based rehabilitation training system. And we want to explore more action to make it more generalized, and adaptive feedback loops. So in this work, although it is an initial result, we actually show that the muscle information actually helps on the motion prediction task. And this kind of biomechanical features are valued for these applications beyond the raw motion. So in order to bridge this AI prediction and physical simulation, this is a key for the digital human modeling. Thanks for your attention, and I'm happy to take any questions.
Any questions? Okay, no questions. Okay, thank you. Okay, so who's the next? Eva. Okay, she's here. Okay, she's here.